All right, we are continuing our study of chapter 4. We are expanding on the idea of finding critical values and using those critical values to find important features of graphs. So in the previous lesson, you learned how to find the absolute extrema, the absolute max, and the absolute min. Today, we're going to talk about something called the increasing-decreasing test. So if you have a function that is increasing, we know as x increases, y increases. So this little interval right in here would be an increasing interval. Yes, that is a little bug climbing a graph. And then our graph is also increasing in that interval here. So what do we know about the intervals when a graph is increasing? We know that the first derivative is going to be greater than 0. And if you're looking at a function that is decreasing on an interval, as x increases, y decreases. So both of these would be examples. What do we know about both of those intervals? Our slope of our tangent line is negative, therefore our first derivative would be less than 0. So our increasing-decreasing test tells us when a function is increasing or decreasing. So we will find the first derivative, and when the first derivative is greater than 0 on an interval, we know the function is increasing. When the first derivative is less than 0, we know that f is decreasing. So how will we go about doing that? Well, we have some steps down here. So the first step is going to be to find the critical values, which we know happens when the derivative is 0 or when the derivative doesn't exist. And then we will create a sign diagram. You guys remember a sign diagram? We used that when we were talking about velocity of a moving object and an object moving forward or backwards. So we'll have some critical values plotted on our sign diagram, and we will test numbers within each of these intervals into the first derivative to determine if it was positive, for example, or negative. And then we will assign any intervals that were positive on the first derivative, we will assign them as an increasing interval. And then any intervals that are negative, we will classify it as a decreasing interval. There is also something called the first derivative test, and it says that suppose c is a critical number of a continuous function. If f prime changes from positive to negative at c, then f has a local maximum. Well, let's think about that visually. If I have a curve that has a local max, I know that the derivative up at the top is going to be 0. On the way up, my slope is positive. On the way down, my slope is negative. So we'll find a critical value, and if we know it's positive before that critical value and negative after, we know we have a local maximum. On your continuum, on your sign diagram, we would have found a critical value here, and we would have found an interval that was switched from positive to negative. That's what this will look like. That's what will tell us we're working with a local maximum. Along the same lines, a local minimum will occur when a first derivative changes from negative to positive. So in terms of looking at it as a graph, if I think about what a local minimum looks like, we would have a 0 slope at the bottom, negative slopes before it, positive slopes after. That guarantees we've got a local minimum there. On your sign diagram, we would be switching from a negative interval to a positive interval. And the third item on here, if f prime does not change sign, so you may have a critical value that you test and there's no sign change around it. For example, it's positive, positive, or maybe negative, negative. Then there is no local max or local min at that point. So in terms of our steps down here, we said we're going to find the critical values. We're going to plot it on a sign diagram, classify whether our intervals are increasing or decreasing. And the last thing is, once we know that we have a local max or a local min, we will find the y coordinates. So a local max will happen if it switches from positive to negative, min from negative to positive. Okay, so let's actually try an example. So I'm always going to start by finding my first derivative and setting that equal to 0. So this would be 12x cubed minus 12x squared minus 24x plus 0. So we're going to set that equal to 0. And while I'm here, I'm going to go ahead and start factoring this. So I know I can factor out a 12x. That's going to leave me with x squared minus x minus 2. So we have 12x times x minus 2 times x plus 1. And I'm going to set each of those equal to 0. So I'm left with x equals 0 when I set 12x equals 0. Here I'm going to have x equals 2 and x equals -1. So I'm going to draw a sign diagram, and I'm going to plot each of my critical values underneath that sign diagram. Just to clarify from the previous lesson, we at that point tested all of the numbers. We were looking for absolute maxima and absolute minima. With polynomials, they go up and down forever. So that's kind of a different scenario. We don't have a restricted domain here. So we're not looking for the absolute max or absolute min. We could find it if we need to. Later on when we're sketching, we'll be identifying the absolute max and absolute min when we need to. But this time, remember, we're just looking for local maxes and local mins. So what I'm going to do is grab a number from each of these intervals, and I'm going to substitute it into my first derivative. If I substitute it in here, I have to calculate a numeric answer. I don't want to do that. I'm going to be lazy. So I'm going to substitute into my factored form. So a number less than -1, like -2. So if I substitute -2 in here, I have a negative number. -2 minus 2 is negative. -2 plus 1 is negative. A negative times a negative times a negative is a negative. So any number in this interval is going to be negative. Between -1 and 0, it'd be like -1/2. So 12 times -1/2 is negative. -1/2 minus 2 is negative. -1/2 plus 1 is positive. So a negative times a negative times a positive would be a positive. Between 0 and 2, that's 1. 12 times 1 is positive. 1 minus 2 is negative. 1 plus 1 is positive. Positive times a negative times a positive is a negative. And then greater than 2 would be like 3. 12 times 3 is positive. 3 minus 2 is positive. 3 plus 1 is positive. The product of all of those is positive. Now in this example, it alternated signs. That does not always happen, please realize. Okay, so what we're going to do, the question is asking us to find our local maxes and our local mins. Oh, actually, it's asking us to identify where we have increasing and decreasing intervals. So our increasing interval would be anywhere this graph switches from positive to negative. Think about it. It's increasing and then it's decreasing. That would be where a local max happens. Oh, we're not finding local maxes and mins. Sorry, we're finding where it's increasing and decreasing, which is actually just the interval between -1 and 0. So my first interval is from -1 to 0, and my next interval is from 2 out to infinity. And then for my decreasing interval, it's anywhere I found the first derivative to be negative. So that would be from -infinity to -1, and then from 0 to 2. Note, I'm not including the actual numbers, so you're not seeing me use brackets on here. The reason for that is at these numbers, my derivative was 0. It was not positive or negative. Okay, if they had asked me to find a local max, because I started to answer that question, we would have found a local max right here at 0. At 2, it's decreasing and then increasing. That would be a local min. And then over at -1, decreasing and then increasing, that would be a local min as well. But tonight, I think you have a combination of both. So I do think they ask you to identify where the points are. So I'm going to go ahead and find it just in case. I can't remember off the top of my head. So we have a local max when my graph switches from positive to negative. So I have a local max at 0. I am going to plug the number in and find the corresponding y coordinate. I have a local min at -1 because I switched from being negative to positive. So a local min at -1, and I'll plug that in a moment, find my value. And then I also have a local min up here at 2. So we'll plug 2 in as well. So we need to substitute all of these numbers in. When you are finding the actual maxes and mins, you substitute back into my original function. So I'm going to come up here and use this space. So I'm going to substitute 0 in. 0 minus 0 minus 0 equals 5. So my local max would be 0, 5. I'm going to substitute a -1 in. So we would have 3 times -1 to the 4th minus 4 times -1 cubed minus 12 times negative 1 squared plus 5. So that's going to be 1 times 3 is 3, negative 1 times negative 4 is plus 4, positive 1 times negative 12 is minus 12, and then plus 5. So we have 3 plus 4 is 7, plus 5 is 12, minus 12, that's actually 0. So we have negative 1, 0. And then our very last local min that we're going to look for is at 2. So 3 times 2 to the 4th minus 4 times 2 cubed minus 12 times 2 squared plus 5. So 2 to the 4th is 16 times 3 is 48. 2 cubed is 8 times 4 is 32. 2 squared is 4 minus times negative 12 is minus 48 plus 5. So our 48's cancel, that's lovely. And negative 32 plus 5 leaves me with negative 27. So we have a maximum at 0, 5, and then we have local mins at negative 1, 0, and 2, negative 27. All right, our next example is an example of an e to the x function. So I'm going to start by finding my first derivative. And my derivative of e to a power is e to the exact same power, but I've got a little chain rule in here. So I'm going to multiply by the derivative of that inner function. So the derivative of negative x squared is negative 2x. There we go. So I'm going to set this equal to 0. So we have, I'm going to just move that negative 2x to the front times e to the negative x squared. And that really is two factors. You can think of this as a factor and this as a factor if you like. So if I set 0 equal to negative 2x, we get x equals 0. There's our first critical value. If I set e to the negative x squared equal to 0. Now, if you think about this logically, e is a number, 2.71828, 2.7-ish. 2.7 raised to a power will never equal 0. If you didn't realize that, though, you would start to solve this by taking the ln of both sides. And on this side, my ln of e would cancel out. I'd be left with negative x squared. On this side, ln of 0, that does not exist. You can only take logs of positive numbers. So this whole factor gets thrown out. So we only have one critical value of 0. So our sign diagram is only going to include one number on it. And I'm testing numbers around this. So if I substitute in, for example, a positive 1, remember I'm substituting it in right here. So negative 2 times positive 1 is a negative number. And 2.7 raised to any power is always going to be positive. But if you just plugged in a 1, 1 squared is 1. That's a negative 1. So e to the negative 1 power just makes a reciprocal 1 over e. That is still going to be positive. So negative times a positive is a negative. If you look at the front interval, less than 0 like negative 1. Negative 2 times negative 1 is positive. A negative 1 squared is 1 times a negative 1 is a negative 1. E to the negative 1 is still going to be positive. Okay, so we've got an interval where this is increasing from negative infinity to 0. We have an interval where this is decreasing from 0 to infinity out here. That's your increasing, decreasing test. And then we're looking for local mins and local maxes. So you look for sign changes. My graph is switching from increasing to decreasing. So look at this physically. That has to be a local max. So we have a local max at 0. So I'm going to substitute 0 back into the original function. E to the negative 0 power, e to the 0 power, anything to the 0 power is equal to 1. So there is my local max. Okay, so you've just seen an example of a polynomial, and you've seen an example of an e to the x function. I've got a couple more examples in here. So I am actually going to jump ahead to example number 4, which is a product rule. This is a harder question. So before you watch this portion of your video, I would make sure you were assigned a question that looks similar to this. If you were not assigned a question that looks similar to this, I would pause, move forward. I would not spend the time watching this. All right, so we're going to find the first derivative, and this is going to involve a product rule. So first function is x plus 2 squared times the derivative of the second, which is 1, plus my second function, which is x minus 1, times the derivative of the first. That's a chain rule. So my 2 comes to the front, my x plus 2 carries down, my power drops down to a 1, times the derivative of x plus 2, which is 1. And at this point, maybe you want to clean this up a little bit. So I would have x plus 2 squared. 2 times 1 is 2. I'm not distributing anything out, and here's why. I'm going to set this equal to 0. And you could distribute. You could FOIL this out, and you could FOIL that out. That works fine. But this is a good point for us to start practicing factoring out what we need instead of distributing, because we're going to have some problems where this power is higher than 2, and you don't want to distribute that out manually. So I am going to look for what this term in the front and this term in the back have in common. They both have an x plus 2, so I am going to factor an x plus 2 way out to the front. And whenever you factor out a greatest common factor, you pick the smallest power. So I have a 2 here and a 1 here. I'm going to factor out a 1. And what am I left with? Well, I'm going to now divide. So x plus 2 squared divided by x plus 2 to the 1. That's what we do when we factor out. We divide. So that's going to leave me with x plus 2. Remember, whenever you divide, you subtract your powers. 2 minus 1 leaves me with a 1. I'm going to take my second expression and divide this by x plus 2. So this 2 carries down. This x minus 1 just carries down, and x plus 2 divided by x plus 2 is equal to 1, so I don't need to write an extra 1 there. And now we'll clean that up. So I have x plus 2 here. In here I have x plus 2 plus 2x minus 2. So we have x plus 2x, which is actually 3x. Let's squeeze that in there. And then 2 minus 2 actually adds up to 0. So we have two factors here. Remember what we're doing. We set our derivative equal to 0. Now I'm going to set each of my factors equal to 0. So setting x plus 2 equal to 0 leaves you with x equals negative 2. Setting 3x equal to 0 leaves you with x equals 0. So I have two values to plot on my number line, negative 2 and 0. And we're going to substitute numbers in these intervals into this factored form. So if I substitute a negative 3 in, negative 3 plus 2 is negative. 3 times negative 3 is negative. So a negative times a negative is a positive. Between negative 2 and 0, we'll substitute a negative 1 in. Negative 1 plus 2 is positive. 3 times negative 1 is negative. So a positive times a negative is a negative. And then for my last interval, let's substitute a 1 in. So 1 plus 2 is positive, 3 times 1 is positive. So if we're asked to identify where this is increasing, that would be from negative infinity to negative 2. So everywhere my interval is positive, and also from 0 out to infinity. You can use the union symbol or a comma is fine. And this is decreasing everywhere my interval is negative. So from negative 2 out to 0. I'm identifying local mins and maxes as well. So look everywhere you have a sign change. Here's a sign change at negative 2. This graph is increasing and then it's decreasing. Look at that graph. I'm seeing a little local max in there. So I have a local max at negative 2. And then over here, it is decreasing and then increasing. So that must be a local min. So I have a local min at 0. So I do need to find the corresponding y values, and I'm substituting those back into my original function way up here. So if I am substituting a 0, and I'm going to come right up to the side here. If you substituted a 0 in here, 0 plus 2 squared times 0 minus 1. So 0 plus 2 is 2, squared is 4. Times negative 1, so that leaves me with negative 4. And then let's substitute a negative 2 in to find my local max. So again, I'm back up here. So I have negative 2 plus 2, quantity squared, and then I have negative 2 minus 1. So that would be 0 squared, which is 0, times -3, which is just 0. So my local max is happening at 0. So we have our increasing interval, our decreasing interval, and our local min and our local max. All right, we've got one last example. So we looked at polynomials and e to the x function, a product rule, and we can't get by without looking at a quotient rule. So the structure of this problem, that's kind of hard to read up here. Let me rewrite that. That says 4x over x minus 1 squared. The structure of this problem is actually written as an IB style question, but I'm going to use this in all of my calculus classes because it kind of gives you a little bit of a hint along the way. What I mean by that is I'm looking for my critical values. So I'm going to start by finding my derivative here. So I'm using my quotient rule. So low, d high, so the derivative of 4x is 4, minus high, which is 4x, d low. So I've got a little chain rule here. So 2 comes to the front, x minus 1 carries down, power drops down to a 1, derivative of the inside, x minus 1 is 1. And that is all over the denominator, x minus 1 quantity squared. So if you'd like to clean this up a little bit, we know we're going to set that equal to 0. If you want to clean this up, I am not going to square this out and expand everything. All I'm going to do for right now is move this coefficient to the front. So 4 times x minus 1 squared. Here I have 4 times 2, which is 8x times x minus 1. And on the bottom, I have x minus 1 to the 4th. Could I expand this out? Yes. But I'm just letting you know that there are going to be some problems where expanding is not an option because this power is going to be too high. So we're going to set this up by factoring. And so when I say set this up, we're going to set this up to solve it by factoring. So in the numerator, I'm going to factor that. And if you look at the question, it says show that the derivative is this. Now look at that derivative and look at what we have. They don't look anything alike yet. But what I notice is that that numerator is factored. So let's look at this numerator. And what do these two terms have in common? They both have an x minus 1. They also both have a 4 that we could factor out. I'm actually peeking up here and I'm seeing they took out a -4. So I'm going to go ahead and take out a -4. And I have an x minus 1. We can take out the smallest power. So the smallest power would be a 1. So what does that leave us with when we divide? So 4 times x minus 1 squared divided by -4 times x minus 1. That is going to leave us with 4 divided by 4 is -1. X minus 1 squared divided by x minus 1 leaves us with x minus 1. Subtract your powers. 2 minus 1 leaves me with a 1. For the second term, -8x divided by -4 is positive 2x. And x minus 1 divided by x minus 1 is 1. So I don't need to write that. And on the bottom, we have x minus 1 to the 4th power. As I start cleaning this up, what I am noticing is that this is in a factored form. I just need to clean that last factor up. But I am seeing that this x minus 1 on top is going to cancel with one of these x minus 1s on the bottom. So it's going to drop that down to an x minus 1 cubed. So on top, I'm left with an x minus 4. On the bottom here, I have an x minus 1 cubed. And then on the top, I also need to finish distributing this out. So we have -1x plus 1 plus 2x. So my last step here, -4 times 2x minus x is x plus 1 over x minus 1 cubed. I don't know why I use a parentheses and a bracket. We'll just make that a parenthesis. And double check against the original problem. We just showed that the first derivative equals that exact expression. So the reason why I like to use this kind of format is you know the format of the answer that I'm looking for. So when we first took the derivative, it didn't look anything like that. So we knew we wanted to either distribute out or factor to make it look like that format. All right, now we're going to draw their sign diagram. So I'm going to come up here. We actually need to find where my factors are, where my critical values are. So I'm going to set my numerator equal to 0. So that would be -4 times x plus 1 set equal to 0. And I'm going to set my denominator equal to 0. And I'm just going to set x minus 1 equal to 0 because the cube just means there's 3 of the same exact factor. So this leaves me with x equals 1. If you divide by negative 4 here, we get x equals negative 1. So we got 1 and negative 1. So on our sign diagram, we're going to plot both of those. And when we plug numbers back in, we're going to substitute it into this simplified factored form. So I'm going to substitute a negative 2 in. This negative 4 is always going to be a negative. Negative 2 minus plus 1 is negative. Negative 2 minus 1 is negative, cubed is a negative. Negative times a negative over a negative is a negative. Let's substitute 0 in. So negative 4 times 0 plus 1 is positive, over 0 minus 1, which is negative, cubed is a negative. So that leaves us with a positive. And let's plug in 2. So this is negative. 2 plus 1 is positive. 2 minus 1 cubed is positive. So a negative times a positive is a negative. So this is increasing between negative 1 and 1. This is decreasing from negative infinity to negative 1, and also from 1 out to infinity. If they ask, okay, so we went a little bit further for part A, but it was draw the sign diagram. So this is part A. Part B says, hence, find intervals where y equals f of x is increasing or decreasing. So this is part B. If you are an IB student, the word hence means use your previous work. So use your sign diagram. If they asked you to justify why this is increasing, you could state that my first derivative is positive, and justifying why it's decreasing, my first derivative is negative. They did not ask me to find local mins and maxes, but I'm going to go ahead and find it since we're here. So do we have a local min or do we have a local max on these? For your local mins and local maxes, you would be looking for where you have a sign change. Now this is a rational function. We haven't spent a lot of time graphing these, but we'll go ahead and take a look. And this is going to pop back up later in chapter 4 when we start sketching rational functions. So if I'm looking for local min, we're looking for where it switches from a negative to a positive. There's my first local min. So I think it's happening at negative 1. So I would substitute negative 1 in. It looks like we might have a local max at 1. So I'm going to substitute a 1 in. I say we might have one because with rational functions, sometimes you have some unique things that are occurring. So I'm going to substitute negative 1 into my original function. So on the top, 4 times negative 1 is negative 4. On the bottom, negative 1 minus 1 is negative 2. Squared is 4. So we have negative 1. So we have a local min at negative 1, negative 1. For a local max, I'm going to substitute a 1 in. So on top, I have 4 times 1 is 4. On the bottom, I have 1 minus 1, which is 0, squared, which is 0. This does not have a local max because the graph is undefined there. And we'll review it later on, but the reason why it's undefined there is we actually have a vertical asymptote at that point. Okay, thank you so much for listening. I went a lot further than you needed for tonight's homework, but I really appreciate you sticking it out to the end. Thank you so much.